Hey guys, welcome to another episode of Live Learning with me, your host, Yujin Tang. So today we're going to be learning about hyperparameter tuning in PyTorch, and we're going to use Ray because this is the automatic suggested library to use. I'm going to drop a link to the library below so that you can understand how to use it. So far in this series, we've learned a bit about PyTorch. Um, we've been working with a fashion MNIST dataset, and we've learned about convolutional neural networks, regular neural networks, and k-fold validation. And in this tutorial, in this guide, in this live learning episode, where I'm going to learn how to use Ray for based on their documentation, um, we're going to learn how to do hyperparameter tuning for the convolutional neural network that we have been building. So we're going to go here. We're going to import this. I wonder if I can import this quietly. Quiet imports Jupyter Notebook. Capture. Okay. You can save the outputs to a variable as well. Interesting. Okay. Well, so the reason I'm suppressing this output is because it always tells me that it's like there's a warning that I can't find the image extension. Now we're going to go and we're going to grab our neural network. Um, Saying that it can't get neural networks. Doesn't seem to make sense. Well, it can, it's just not recognizing them. So let's clear out these comments. I don't think we need them anymore. We've done this exploration now. Cool. Cool. Nice. Now the next thing we need to do is we need to do Ray. We need to do the Ray imports as well. So we're going to import Ray. From Ray, import tune. From ray.tune, import CLI reporter. This is going to report things in the CLI, I assume. From ray.tune.schedulers, import ASHA scheduler, async hyperband scheduler, async successive halving. All right, what's going on here? No module named pandas. I didn't even know I didn't have pandas in here. Okay. Let's also pip install pandas. This is why you use virtual environments. Thought I had pandas installed in my environment, but I did not. Oh, okay. Now I'm gonna do that. Any other errors? No matches found. Ray tune. Okay, this is an error. This is a problem. Okay, so Z shell treats this as the brackets as special characters. So what we're going to do is we're going to do this. This is not right. Okay, quotes, single quotes. Huh. Cool. Now we can import Ray. So we're also going to create a couple data loaders. So this is very similar to the PyTorch tutorial, but they're using the CFAR dataset. We're using the fashion MNIST dataset. So we're going to create a function, load data, and we're going to give it a directory, fashion MNIST. This is just going to be the automatic directory, but we can also choose to change this up if we need. This just makes the default load to that directory. To tensor. Equals string set equals don't need this. Data sets, yeah, okay. Training data, testing data, test set equals this. Yeah, okay. Oh, return. Cool. We have the neural network already. Now we're going to have to create a train function. So here, we're going to create def train network. Config checkpointer data equals none. Actually, I'm not sure we need a config here, but we're going to figure out what we need here in a moment. So first we're going to, actually what we should do is we should get rid of this stuff here. This should not be here. And put it in here. So actually, what I should do is I should restart the kernel so that we don't have any models laying around. Cool. Now, model.toDevice. ToDevice, is that right? To CPU. Oops. Yeah. Now, if checkpointer, this means that we've already created a checkpoint for our model. We should do model state optimizer state equals torch.load. So last time we showed how torch.saved works with, I guess the capture thing makes it so that it doesn't recognize that these are imported. But anyway, we saw these as different folds trained. So we saved those earlier with the kfold.save. Kfold.save, save. Right here. And now we're using now we're using torch.load. Sorry, we used torch.save. Now we're using torch.load. This is not loading the kfold validation models. This is loading the checkpoints. Path.join checkpointer checkpoint. So we have to import OS. Oh, it's already imported. Okay. This is kind of weird. Okay, maybe I'll just get rid of this because it's just making it annoying to. Oh, it's not giving me an error this time. Okay, fine. I don't know why it was giving me an error before. Model.load state. Model state. And then optimizer.load state. Optimizer state. And that should be it. What is it giving me this? What's going on here? Why is it giving me this red line? Oh. Ha! My tabbing was off, yeah. Now we're going to load the data set. So training data equals load data, testing, training data, testing data. Oops. Now we're going to split the subset. We're going to split the data set into training and validation data. We're not going to do k-fold this time. We're just splitting the data set. And we'll probably add k-fold later on. So, val idx, oops, equals int len training data 0.2. Training data validation subset equals random split. Oh, what did I use last time in k-fold? torch.utils.data.subset. Oh, the indices. I think we can just use random split. Let's see, PyTorch random split. Torch.utils.data random split. Oops. There we go. Random split into train data into a list of val idx. Maybe that's not the best name for it. Nice, val idx. Now we're going to do the train loader, train data loader. And we're going to set that equal to data loader training subset batch size equals, I'm going to call this batch size just batch size. Batch size. I could just say 64, but val data loader equals same thing except validation subset. Yeah, okay. Now we're doing the optimization loop. So notice in the last couple ones we split the training, the validation, and the training, the optimization, and the accuracy testing. This time we're just putting it all into one. So my challenge to you is, how would you do this in the same way that we did it before? And we'll probably take a video on that before as well. We'll take a video on that later, sorry, not before. For for I comma data and enumerate train loader. Sorry, train data loader. Inputs labels equals data, because remember the data is 2. It's a tuple of 2. It's got the training data and then the actual labels that it's supposed to have. And now let's put them to the device like we do with the models. Actually, I don't think we even need to do that. Well, let's do it anyway, because we already did it beforehand, so I guess we'll just do device equals CPU. We don't want to have any magic strings anywhere, so press shift enter. Optimizer 0 grad. So we zero all the gradients. Now we're going to do the forward pass, the backward pass, and optimize. Okay. So outputs equals model input. Inputs. Loss equals loss function. Outputs. Labels. No, I press shift enter again. Loss dot backward. That's the backward pass, and then optimizer dot step. That is the optimization step. Now let's check out so this is forward pass plus backward pass, back prop plus optimization step. This is printing stats. So running loss is going to equal loss.item. So that gives you the what the item that's in the loss. Epic steps plus equals 1. For epoch, and yeah. And now we're gonna do. So earlier we were doing 100 mini batches. This time we can do mini batches and whatever. So if I 100 is equal to 0, mini batches of 100. We'll print out the loss function. So print epic I, and then running loss over epic steps. Five? 8F. Okay, well, we can do 5F, doesn't matter. It's just telling you how many floating points we want to show. And then we reset running loss to 0. Now we check the validation loss. So let's check the validation loss, validation functions, functionality. val loss equals 0.0. Number of val steps equals 0. So in each epoch, we're checking the validation and the training. So that's kind of interesting, a little bit different. I suppose it makes sense with hyperparameter tuning. You want to be able to kind of play around with your tuning, but it actually doesn't have to be done this way. You can do an entire 10 epochs of training and then check your validation loss. That's usually when you test accuracy at the end, I guess. But yes, so this is one way that you can check your validation loss as you're training. Correct equals 0. And then once again, for I data in enumerate validation loader. Where's my validation? Val loader. With torch.noGrad, as we did last time. Oh, my neck. Now we do the outputs. Outputs are equal to the model inputs. And then we'll look at the predicted labelings, so we don't actually care about the rest of the model, or less the rest of the outputs. Let's torch that. Max puts.data 1. So remember that the neural network is going to put out a set of predictions for what the outputs are. So the reason we're doing the predicted is because we want just the max value of those outputs. Okay. Equal labels.size. Labels.size. Yes, okay. This puts us at this as the first function, the size of the labels, basically. This is how we know how many total we're predicting on. And now we're going to predict correct is going to be equal to the predicted equals labels. Predicted equals labels. Sum item. So this gets the sum of all of these where this is where the predicted is equal to the labels, and then we're getting the actual value with a dot item. So now loss is going to be equal to loss function. Oops, fun. There we go. Loss function on the outputs and the labels. And now validation loss is going to be equal to, plus equal loss.cpu.numpy. Val steps is going to increment by 1. So I don't know what this does. Don't know why. I think this sends the loss to the CPU and then does it in NumPy, but we're already using the CPU, so I think we can just do loss.numpy. If you were using the GPU, you probably want to do loss.cpu.numpy. Now that we've done this, we want to go and make a checkpoint. So with tune.checkpoint, checkpoint, dir epic, yep. As checkpoint dir, we want to set the path because set path.join, checkpoint, checkpointer, checkpoint. And now we want to use save again like we did last time. Sorry, model.state, I believe, state dict. and optimizer dot state dict. And I want to save this to the path. Oops. And then we want to tune dot report. We want to get a report out of this. Loss equals val loss over val steps. Accuracy. Am I spelling this right? Accuracy equals correct over total. And then that's it. So this is what the hyperparameter tuning should do. And now what we want to do is we want to be able to pass multiple test spaces. So we'll have to pass multiple trials here, but this will take a second to implement the configuration. So I have to go back and implement the configuration file. So let's see, where is that? Into the init. So here we go. Earlier we said we might not need a config. We need a config for the array stuff. So that is why this is imported. Cool. So L1 equals 64. L2 equals 64. So we're gonna need two different. Let's do 128. Well, let's do 128 here. 128 linear. 128 64. Ah, I did forget a comma. Thank you. Okay. So this should actually be L1. This should be L2. So now we can have a neural network config L1, config L2. So we're going to pass these in as dictionaries, and we're going to train them. So once we have that, we're going to test it. So this is the training network. This is the testing network. Test accuracy. Net. So model device equals CPU. And then training data, testing data equals load data. The test loader equals data loader of the testing data. That's not what I wanted to do. Testing data, there we go. Batch size still has to equal 64. Shuffle equals false. Okay. Now we'll do correct equals 0, so measure. Total is also equal to 0 with torch.nograd, just like we do with validation. Data in test loader. We'll do the images, labels. It should be inputs probably, but it doesn't really matter. Now we'll send them to device. I'm going to continue making this inputs just for clarity and continuity's sake. Outputs. Outputs is equal to the inputs, and now we do the same thing we did in the validation check. So torch.max outputs.data 1 total plus equal labels dot size 0, and the correct is once again we're going to add where the predicted is equal to the labels sum dot item. Cool. Oh, that's not what I meant to do. Click the wrong thing. And now we're going to return correct over total. So now we have our main functions set up. Now we need to define a space. So config. We need to define a config space to search. So this would be L1. Oh, should we have a different learning rate? I set the learning rate earlier, but in their example, they also show that you can do a different learning rate. But we're just gonna you can also tune the batch size, but we are going to just tune L1 and L2. So tune.sample from lambda. I think lambda functions are actually considered best practice in Python, but rand int 29. Oh, I don't have NumPy imported. Okay, so let me import NumPy as np. Random.randint. Cool. And then L2 tune.sample from lambda to the np.random.randint 29. Oh, I forgot to put a comma here. Cool. So now we can basically have a result run with where we can use ray.tune to run this trial that we're running here. Partial. What are they? What is this? The training function, which I call train network. Train network. And nothing on the data there. I don't think it matters. Where is this? Oh. That should be wrapped with func tools. I don't have func tools either. Cool. The data dir, where did I put that? Yes, it should be the same. I don't think that I need to do that. Config should equal config. And checkpoint at end should equal true. I'm not sure if there's anything else I need to set here. So, okay. Oh, this is just running it, and I'm running into errors. Dataset not found. Excuse me? What? 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 Why is it not finding the dataset? It had trouble finding this? Oh, okay. Dataset still not found, huh? Trials did not complete. Okay, so this is going to take more time than I thought. Cool, so going to pause this and come back to this later. Okay, so I actually got this to work by just passing the absolute value of the date of the data set, which should have been dot dot slash dot dot slash fashion MNIST, but I had to pass the full value to it. Now, my issue with this is that we are seeing this using like a dark background. So going to change the I've been in dark theme for so long. But this does not super well fit dark theme. I'll put to a file. Send Jupyter Notebook. Put it to a file or Jupyter Notebook Reporter Array. Well, I'm not going to make you watch this whole thing, but we will come back at the end and we will discuss how the trials go. Okay, so in almost 16 minutes, it ran through exactly 300 something iterations, 400 something iterations. Trials did not complete. Yeah. Probably because there's a lot of things to train, but also because there are a ton of configurations to run. So my suggestion is don't run hyperparameter training with a CPU unless you can. Just do it on a GPU. I do not have access to run. Well, maybe we'll figure that out next time. We'll see if I can get the GPU to run. But this is it for hyperparameter tuning because I'm not going to sit here and wait 20 hours for this. Thanks for watching. Remember to subscribe, and good luck tuning your hyperparameters on your models.